Okay, we are back for the lab part. So Aurora, go ahead.
Okay, great. So I think that Esteban sent you all a Google document or just a Word document that has kind of what I was hoping to get through today. And today we're going to be working on exploring spectral data from public archives and how to access this, how to plot up some things, and then at later classes we'll actually kind of analyze it. But today we're just accessing and doing a little bit of plotting. Okay. So I'm going to share my screen, and if everybody could open up the Word document, we'll kind of follow that step by step. And there's the links that you'll need for the Word document, in the Word document, for some of the websites that I'll be using. So I'm going to share my screen now, and okay, so now I think that you can see my whole Google Chrome. And we're going to be using a Colaboratory, which is a Google environment that allows you to do Python programming. So if you go to the Colaboratory link that's in the Word document that I sent around, a page kind of like this will pop up. And you should see something that says New Notebook, and you can click on that. And I've created this notebook called Workshop 1 Example. And Esteban shared the link with you all in the YouTube. And so you can use that link to follow along and have the example that I do, so that you can use it as an example to copy for when you're doing some of the exercises on your own. Okay, so here is the worksheet that we'll be using. So we're going to be looking at data from a few different public archives today, the Carmenes Archive, the HARPS Archive, and the HiRes Archive. So these are three different near-infrared spectrographs. These are three different high-resolution spectrographs. Carmenes has a near-infrared channel and a visible channel. So you get to see the difference between some high-resolution near-infrared data and some high-resolution visible data. HARPS is high-resolution visible data, and HiRes is also high-resolution visible data. And yeah, like I just said, we'll be doing all of the plotting with the Google Colaboratory, which is a Python notebook. So you can use this link to go here, create a new notebook, and do your own. And also you can follow along with my Colab example worksheet here. Okay, so we're going to start by looking at the high-res data. So if you want to, I'll just do this live. We can copy our link. Great. And so this is the Keck Observatory Archive. And this has all the public data that is available with Keck. And so we're interested in, there's visible data, there's near infrared data. And like I said, we're interested in high-res. That's the high-resolution spectrograph. So we can get rid of the rest. They do have a near-infrared high-resolution spectrograph, NIRSpec. It's only resolution of about 25,000, so it's not quite as high as the other ones. But we won't look at that today, but you can look at it, and all of the data, most of the data is publicly available here. So we won't look at that today. And then in order to search, you can either search in a date that you want, or an object name, or a coordinate, or anything like that. And one of the ones that we will search for today, you can see I've searched for lots. We'll look at WASP-33. So WASP-33 is a hot Jupiter, or is a star that hosts a hot Jupiter. And so since I do exoplanets, I mostly use all of this stuff for exoplanets. So that's what I know. So we'll just look at that for now. And it can resolve the names of your objects. Anything that you would type into Simbad, it should also be able to resolve here, and then it'll give your coordinates and search for the correct thing. Okay, so then we can just say search. Okay, so up here, this is in order to download things, and we won't download anything from HiRes today, but if you do want to download things, or if you're doing a really big search, you can make an account here, and they'll just email you when your files are ready to download. But it's listed, you can see all of the spectra. There's 222 total spectra of WASP-33, so lots of spectra. And you can download them. But what's cool about this data archive is that you can just do a quick look of the spectra. And so you can see I've clicked on this before, but I can do a quick look of the extracted spectrum. And that opens here. And we can look at our high resolution spectrum. They show a bunch of different plots. So yeah, here's some orders, and you can see all of the orders have kind of this characteristic shape, which we'll go over tomorrow, why the orders have this characteristic up and down kind of shape. But if you want to zoom in, they're showing some absorption features at high resolution from the star. And so there's a really nice quick look, so you can just make sure that it has the right wavelength coverage that you're looking for and stuff. Oh, and it tells you about the signal to noise, so you can see, oh, our signal to noise around 4,000 angstroms is about 80, so that's pretty good. And there's lots of plots. Here's some more plots. More plots. So, yep, that's what you can get from Keck. So just so you know that that's there and kind of know how to go through and look for the stuff. So next, what we'll actually be playing with, the data we'll actually be playing with first is from Carmena's. So you can just copy the Carmena's link, paste it in a new tab. And here now we're at the Calar Alto archive webpage. And it kind of has a similar type of format where you can type in your object name, your search radius if you're typing in coordinates, so things that match within that search radius. And dates that you want, and then what instruments that you want. And we're going to be looking at WASP-76. Again, this is another exoplanet host star. And yeah, we don't care about the dates. And we don't want anything from the 2.2 meter telescope. We only care about the Carmenas. So we can uncheck all of the other instruments. Okay. And then I already know that there's lots of spectra of WASP-76. So we'll just up this to 250. And then we can submit our query. Okay, it's taking a bit of time. Oh, there we go. Okay. So yeah, you can see just how many spectra we have. And they're all of WAS76, just taken at different times. And what you need to look for here is, like I said before, Carmenes has both a near-infrared channel and a visible channel. And so this is telling you whether you're going to be looking at the visible or the near-infrared. And here we have the observation date, the exposure time, and then I asked for it to return both the raw data and the data that has already been reduced. And so that's why here I'm showing all of the raw FITS files. And here, this is the final science data products. And for today, we're going to be downloading the final reduced science data products to be plotting. So this is the data that we're going to be looking at today. So it doesn't really matter. Yep.
You have a question here on YouTube.
Okay.
Why are there so many rows of data for the same astronomical object and instrument, for instance, in the Keck data?
Yeah. So there's so many spectra here of WAS76 because later when we talk about how you use high-resolution spectroscopy or what you use high-resolution spectra for, a lot of what this is being used for, so WAS76 in particular, people are looking for exoplanets around these stars. And to find an exoplanet with the radial velocity technique, you need to take spectra at lots of different times and then find the radial velocity wobble of the star. And again, we'll go into this in detail, but basically you just need a lot of high resolution spectra in order to detect exoplanets. And so that's why there's so many spectra of all of these exoplanet host stars. So on the high res, WAS33 is also an exoplanet host star. And in order to detect the exoplanet, you need lots of spectra. Okay. So, yeah, it doesn't really matter which spectrum you want to download, but if you, everybody should try to download one visible spectrum and one near infrared spectrum, and maybe something with a longer exposure time. So don't download one of the ones that's like 7 seconds. Download one of the ones that's 600 seconds or so. So I will show you. Let's see. Here is a nice visible one, and I just click the FITS, and it downloads. And I will do the same thing for the near infrared. And now I've downloaded 2 zip files that have the near infrared spectra in them for just a single time. Okay, great. So now let's plot that. Okay. So once everybody has downloaded their spectra, I'm going to be working in my collaboratory, that's what's called, collaboratory notebook. And you can follow along, but I want you to do your own as well. Okay, so I'm new to collaboratory as well, but I've done a run through of this and it seems to work okay. So hopefully there won't be any glitches. So in order to, when you download the files, you're going to get them in a FITS file format. And if you're new to FITS files, that's okay. We'll do a brief introduction. But in order to open and manipulate FITS files, I use the AstroPy library. So we can import things into our Python environment here. So from astropy.io, we'll import FITS. And then we've just downloaded the file onto my computer or onto your computer, and we want to upload those into the collaboratory environment. So to do that, we do from google.collab import files. And we can now upload a file from our computer. And in this environment, this is kind of like a Jupyter notebook, so you have to just press run to run your code. So then it's going to ask me, hopefully. Oh, I need that. Okay, great. So now it's going to ask me to choose a file from my computer, so I can choose one of the files I just downloaded. So when I downloaded it and unzipped it, let's see. Okay, so I downloaded one that's visible, we'll look at first. And it's asking me to choose a file from my computer. And in the folder that you unzip, there's going to be a file called either viz or near infrared _a.fits or viz _b.fits. And we're just going to be looking at the A file today. And later when we talk about how you reduce high resolution spectra tomorrow, you'll understand what the A versus the B file is. But for today, we'll just look at the A file. Okay, so then it uploads a file here, and I have to wait for it to upload, so it's 14% done. And this takes a little bit of time since it's a full spectrum at high resolution. Okay, so now it says that it's 100% done. So I'm going to add a new code box. And now let's open the file with AstroPy. So we also need this IO package. So I'm going to call my FITS file F, very creative name. And we'll do fits.open. Oh, and this is nice. It tells me what type of parameters I need here. So for the AstroPy FITS, you need the name of the file, and then you can have a bunch of other arguments, but we don't need that. So then to open it, I have to do io.bytes io uploaded. And then the name of the file that I just uploaded, which is here. And let's hope that that works. So to see if it works, I'm just going to quickly print out the header. And I'll explain that in a second, but let's just see if I did it right. Okay, cool, it worked, yay. Great. So for those of you who have not used FITS files before, FITS files, I think it stands for Flexible Image Transport. Here, like it says, Flexible Image Transport System. And basically, it's what a lot of the data files in astronomy are stored as. And what's really nice about FITS files is you have all of the data, but you also have all of this information that's in the header. And so it's kind of a similar way that you access any NumPy array or list or anything like that in Python, where you have your object and then you have different extensions. So the 0th extension is often where some of the image data will be stored. And that's where the main header is going to be. So if I do the 0th extension and then say I want to look at the header, it'll tell me all of the information about the spectrum. And this header is really long and it has a ton of information. So some important things to look at are check to make sure the object is the one that you think you downloaded. So we wanted WASP-76 and it's listed as WASP-76 here. It tells me the right ascension and the declination of the object. So it's sometimes good to check to make sure, if this is from a public archive, it's probably correct. But if you're just using somebody else's data, make sure that they labeled it correctly. So check that WASP-76 is at this right ascension and declination. And then there's lots of other information here that's just good to know. For example, you can see how long this is. It gives you the signal to noise ratio of each order. And so the signal to noise ratio of order 0 is really low. So you probably don't want to use order 0. But we can see that the signal to noise ratio, oops, sorry, I was wrong. I said it's 0. Its signal noise ratio in order 0 is 118. And as we get to different orders, you can check the different signal to noise ratios. Yeah, lots of other information. You can look through this yourself and kind of see what other information they give you here. So this kind of makes it hard to scroll. So I'm just going to comment this out now. Oops. Okay, great. And now I'm going to add more code. And so what's kind of annoying about FITS files is that each observatory and inch instrument stores their data in a different way. And they don't really tell you how they store their data. And so you really have to go through each file and try to figure it out yourself. So that's what we'll do now. So we can just kind of see how many extensions they have. So we saw that the header contained all the information, but we don't know if maybe there's a first extension that has some of the data or a second extension. So let's just print how long this is. Okay, so it's has a length of 5. So that means that there is a f of 0, an f of 1, an f of 2, an f of 3, and an f of 4. And we don't know what's in each of them. So let's print the header of each of them. F of 1 dot header, and try to figure out what is in that. Okay, so now we get the header for the first table. So f of 1 is our first table. And this tells us that the name of this extension is called spec. And so that means that that's all the spectral data. That's the spectrum is in this header. And it also tells us that it's a 4096 by 61 data array. So it's a 2-dimensional data array. Okay, so there's 4 other extensions. So let's just check them all. Okay, so now we have something called cont, which is continuum. We don't need that now. Then we have something called sig. This is the sigma or uncertainty. So this is, any sort of uncertainty or error array will be stored here. And last, in extension 4 is the wavelengths. And so that's going to be stored in 4. Okay. So then let's just take a quick look at some of the data. So now we know that f of 4 should have the wavelengths. So now instead of looking at the header, we're going to be looking at the data. I'll just make a new box actually so that this doesn't get erased, so that if you look back at this, you can see. Okay. So we want to look at the wavelength data. Okay, and so it has a giant array, and it's arrays within arrays, which is kind of confusing. And they don't tell you anything about what units it's in. So you kind of have to figure that out for yourself again. Since we know that we're looking at the visible arm, so it should be something like something around 500 nanometers or something. So we can figure out what the wavelength unit is here. So this is 5 times 10 to the 3. So 1, 2, 3. So that seems to be in angstroms, since we have something like 5,000 angstroms should be visible light. And you can see that the wavelength coverage goes from about 500 angstroms to about 1,000 angstroms. So that's just right at the very beginning of the near infrared. And also, let's try to see what shape this one is in. Let's just see. What is the length of this? And then, since we know it's arrays within arrays, we can see what's the length of the first element. Okay, so it's telling us here that data has a length of 61, and that data 0, so the first of those 61, has a length of 4,096. And remember, that's the same data that we see up here, 61, 4,096. And so that should have been the same length as the spectrum. So that's good, just to double check that your wavelength arrays and your spectrum arrays have the same dimensions. So what this 61 here means is for high resolution spectra, they usually give you the whole spectrum with the orders still intact. So this means that there's 61 orders in this spectrum, and each order has 4,996 pixels per order. Okay, so let's now visualize this a bit. So we're going to import matplotlib. And matplotlib is the Python plotting program. So let's just plot a single order. So you just do plt.plot, and we'll plot the wavelength on the x-axis. So I type that first. And let's just plot maybe the 10th order. Oh, and now on the y-axis, I want the spectrum data. So that is stored in the first extension, if you remember. Okay, let's run that and see what we get. Oh, great. Okay, so we get a spectrum. And you can see it's a bit noisy at the ends of the orders. And we have wavelength coverage from 5,600 to 5,700. And we can just plot different orders and check it out, see what they look like. Here's 12. And remember that your spectrum might look different than my spectrum because we just randomly downloaded some data. And then another thing that we want to be able to do is to zoom in and out of different regions so we can set the limits. So let's say we want to just look at the center. So 6220 to 6260. Great. Okay, so we've kind of gotten rid of some of the noisy ends of the spectrum, and now you can actually see that we have a high resolution spectrum with some absorption features along here. Cool. All right. And last, I wanted to have you guys do a quick for loop so we can plot all of the orders together. So if you are new to Python programming, you can basically, it's similar in most languages where you do a loop, but you can basically have the computer do the same thing over and over again a certain number of times. So to do that in Python, you can do something like for I in the range. So we want it to do it every time for the whole length of the data. And then you have to indent it when you're in the for loop. So we're going to just plot the wavelength for the ith element. So this will be the first time it goes through, it'll put 0 here. The second time it goes through, it'll put 1. And it'll just do this really quickly, all in order. Okay, great. All right, so this is what it looks like. And you can see that my spectrum is really noisy. I did this on my computer and earlier, and I had a much cleaner spectrum. So I downloaded something with a higher signal to noise. But let's zoom in anyways. Yeah, it looks like there's some bad pixels here where you can see. Oh, I don't have it anymore. When we printed out the wavelength data, there was like a few random negative values at the beginning where there's just, a mistake or something in the pipeline, or it went to a bluer wavelength and the pipeline knows what to deal with, so it just fills in -1. And this is kind of what you have to deal with when you're getting data from the archive, is you have to figure out what happened, and it's always different. So yeah, we don't want to look at all of this because this is not supposed to be here. So let's zoom in to 5,500 to 10,000. Okay, and then it still looks like I have a few random noisy things happening here, which is ruining the rest of my spectrum. So I'm just gonna not look at that. Let's see. And now I will set my Y limits so that I can actually see what's going on. Okay, so you can kind of see spectral data, and I can keep zooming in and try to make this look better. Okay, yeah. So if you've downloaded a nicer spectrum, you can make nicer plots. I've seen to have downloaded a kind of noisy spectrum. That's okay. So that's kind of what you have to do when you're looking at spectral data. So next, I want you to try to do the same thing on your own, but with the near infrared data that you've downloaded. And so you can copy kind of the same thing in some of these questions and plot a single order and plot multiple orders and kind of try to compare what looks different between what looks different between the visible spectrograph and the near infrared spectrograph. What's the wavelength coverage of both of them? And I will let you guys do that on your own for a little bit, and then I will plot up my results and show that to you in a little bit. So let me stop sharing my screen. Okay, I'm going to just turn my camera off and let you do that, and let me know if you have any questions in the chat. And then in maybe 10 minutes, I'll come back. Oh, I forget when the next break is.
Yeah, hi, Aurora. It's now.
Okay.
Yeah, what we can do is that we can leave this 15 minutes. I think it's 15 minutes break. Yeah, you're 15 minutes ahead. So it was supposed to be at 11:50. At 5:15 your time. The break, but what we can do now is that we can leave these 15 minutes. We will be back in 15 minutes. Yeah, sorry for the redundancy. And people can download the data. And in the meanwhile, we will just go for the break, and we will be back in 15 minutes again. And they can start the exercise. So we will be online. You will be answering questions, and the idea is that they reproduce what you have just showed them, right?
Yes, with the near infrared data instead of the visible data. And then we'll also quickly look at a second telescope and try to compare the HARPS data to the Carmena's data, if we have time.
Perfect. Yeah, absolutely. So let's convene at our time, 11:20, your time, 5:20. So in
Perfect.
18 minutes.
Okay, sounds good.
Okay, perfect. See you in a while.
Bye.